That's Jessica.
Awesome. Perfect. Hi, everyone. My name is Jessica Zerb, and I am a master's student with Piyush Jain and Mike Flanagan as supervisors. And my project is forecasting FWI indices using recurrent neural networks and atmospheric teleconnections. Sorry, let me just get rid of this pane here. Okay. All right, so I'm just going to go over a brief outline to give some structure here. So we'll start off with a purpose, touching on machine learning and fire science, current predictive model limitations. We'll go on to the introduction, talking about recurrent neural networks, the data I use for my model. We'll touch on methods, where I used an LSTM model. I use teleconnections as covariates, and model training and testing. We'll move to results, where I show the model results, compare with climatology, and then show the errors, and then the conclusion. All right, so machine learning in fire science is still a relatively new field, and Jain et al. States that a total of 300 papers have been published on the use of ML in fire. However, those are mostly focused on fire occurrence, susceptibility, and risk, and there's been little research that's been done in fire weather and mapping. Jain et al. Also states that ML has been particularly underutilized in fire management with respect to predictive and prescriptive analytics. So this essentially suggests that there is an opportunity for enhanced fire weather forecasting using ML. So right now, monitoring and the short-term forecasting of fire weather really depends on the use of observed surface and upper air weather models, as well as numerical weather prediction systems. On the other hand, seasonal forecasting of fire weather has been largely reliant on global circulation models. Unfortunately, these global circulation models may actually lead to large uncertainties in the prediction of surface meteorology, and this can result in low predictive skill for fire weather indices like the Canadian Fire Weather Index system. And so to resolve this, large-scale atmospheric patterns, otherwise known as teleconnections, are frequently used to predict seasonal variations in weather. So in this project, we consider a deep learning and data-centric approach to predict fire weather indices on a seasonal timescale, so 1 to 6 months. And this approach uses teleconnections like the El Nino Southern Oscillation, the Atlantic Multi-Decadal Oscillation, the Arctic Oscillation, and the Pacific Decadal Oscillation. And we use these teleconnections as covariates within the machine learning model. And that particular model is called a long-term short-term or a long short-term memory neural network. And it's catered to forecasting time series. But I will touch on that a little bit later. Okay, so here's just an example of a simple neural network to give some background. So we can see that it contains one hidden layer, and that's shown in red. And all the inputs on the left side are connected to a neuron, and each of the neurons are just shown by the red circles. So a neuron will accept the inputs, and it applies a regression function and an activation function, and then it'll output a single value. So to simplify this, we can essentially say that a neural network is really an excellent tool for pattern detection, and it's also just an optimization problem. So I have just shown a simple neural network, but for this project in particular, I'm using a little bit more of using a more complex neural network, and it's more complex in that it contains various hidden layers, and they're specifically designed to work with temporal data. So this type of neural net is known as a long short-term memory recurrent neural network, or just known as LSTM, and I'm just going to refer to it as LSTM from now on. And LSTM was developed to reduce computation time and error propagation. And as stated by the creators, Hawkrider and Schmidt-Huber, LSTM solves complex artificial long time lag tasks that have never been solved by previous recurrent neural network algorithms. All right, so what exactly is needed for an LSTM? Well, we can think of an LSTM input as a sliding window across temporal data. So in this example, we input 3 consecutive monthly averaged BUI values, as well as the expected next month's value. And then for the next input, the window slides by 1 month, and we input the following 3 monthly average BUI values, and then the next expected value, and so on. So this will effectively repeat, and this is just how we train the model on all of our available data. But in practice, for my project in particular, we're using larger time steps as inputs. So rather than 3 months, we're using either 12 or 6-month intervals. And the reason that we choose to use 12 or 6 months is because we're using the buildup index as a predictor. And as you know, BUI is heavily reliant on DC, so it does retain the seasonal pattern, which shows up in 6 to 12-month intervals. And so, in other words, we can say BUI serves as the most effective candidate for forecasting because of its seasonality. And so we calculate our BUI data from the 5th version of the European Center for Medium Range Forecast, or just the ERA5 data. And the ERA5 data is from 1950 to present. It provides hourly estimates of oceanic, atmosphere, land, climate variables, and the data covers a 30-kilometer grid and resolves the atmosphere from the surface to 80 kilometers. But in particular, we use the data to calculate monthly averaged BUI values for each ecozone from 1981 till 2019. And it'll, of course, be updated to 2020. And like I had said before, just to reiterate, BUI retains a seasonal pattern. So this is why we use it for the LSTM forecasting. Okay, so now we'll go on to talk about the methods of our LSTM model. So this LSTM model forecasts monthly average BUI values for each ecozone in Canada. We use the past monthly average BUI for forecasting, and this is very similar to climatology or using climatology for forecasting. But because we're using a machine learning model, it allows us to input causal data as a predictor. And so, as mentioned before, teleconnections are frequently used to predict seasonal variations in weather. So we use the teleconnections ENSO, AMO, AO, and PDO as the covariates in the model, and this is just our causal data. These oscillations are essentially large-scale anomalies that result in meteorological change that occur a long distance apart in terms of both time and geographical location. So here is just an example of the El Nino oscillation. It's a sea surface temperature anomaly near the equator in the Pacific Ocean. And the meteorological effect of the El Nino is seen on North America approximately 6 months following the event. So we also use 3 other teleconnections in our model. We use the Atlantic multi-decadal oscillation, which is in the North Atlantic on a period of 60 to 80 years. And it's just shown in red. Then we use the Pacific decadal oscillation, which is on a period of 10 years. And finally, we will use the Arctic oscillation, which is just rather than a sea temperature anomaly, it's a sea level air pressure anomaly, which is centered at the poles. And so aside from choosing covariates, we must also hyperparameter tune the model. And this is done by choosing how much data to train and test on. So currently the model is training on 80% of the data, which is from 1981 till 2011, and testing on 20% from 2012 to 2019. But it can also be tuned by adding hidden layers, and this can improve node connectivity and also prevent from overfitting. Additionally, we can also choose the nonlinear function that the nodes apply to the data itself. And then finally, we can also choose the number of layers, nodes, and model epochs. And right now we're just using a random approach to optimize the problem, but we're still in this phase, so this will probably change. All right, so for results, this first plot shows the comparison between the model prediction in red and the observed BUI values in blue in the boreal plains. And then the second plot shows the same comparison just from the plains. So we can see that the model does a relatively good job at forecasting the appropriate highs and lows, but it is really hard to say until we see more comparisons. So in this next plot, we're doing the same values, but compared to climatology, and climatology is shown in green. So this is for the boreal plains, and then here is for the plains. And so with this comparison, we can actually see that the model does a better job at capturing those extreme values. So if you look at the boreal plains plot in 2015, you can see that the predicted does a better job at forecasting that high extreme value. Likewise, on the lower end of the BUI values, if you look at the plains graph on the right in 2014, again, the predicted is closer to the observed value than the climatology. So here's just another way of comparing that same data. If the model prediction was 100% accurate, it would follow along the blue forecast trend line. Of course, it's not 100% accurate, but we can see that the red scatter plot, which is the predicted model, is closer to the forecast line in the extreme cases. All right, and here we just have a training and validation loss curve for both ecozones. And this is just to ensure that the model is not being overfit or underfit. And this is just standard practice when training machine learning models. So in both instances, the training loss declines rapidly, and then it begins to follow the validation loss curve. And this is a sign of a really well-fit model. So technically, a well-fit model is identified by a training and validation loss that decreases to a point of stability, and then there's minimal gap between the two final loss values. Okay, and finally, here are the mean standard errors and mean absolute errors of the predicted model versus the climatology. So for the boreal plains, we can see that the model is less than the climatology, showing, that it's doing better at predicting than climatology. And here's the same comparison for the plains. So again, the model performs better in both instances of mean standard error and mean absolute error. Okay, so in conclusion, machine learning can be a quite useful tool for predictive modeling and forecasting. And as shown in this research, it can actually outperform traditional long-term forecasting methods. According to Stocks and Martel, the highest financial expenditure in fire management is on the response phase. So advancing the research in weather prediction may work in favor of mitigating these costs. And while machine learning may not replace forecasting practices entirely, it can absolutely be used as an additional tool for validation. And we'll just touch on some future work. So I will continue to do some hyperparameter tuning. We will experiment with different model configurations and hopefully submit a paper, but I need to defend my thesis first. And here are just some acknowledgements. So I'd like to thank everyone that has supported me throughout my research at the U of A. Thank you to the Canadian Partnership for Wildland Fire Science for the ongoing support and helping to make advancements in machine learning in this field. And finally, I just want to say a very special thank you to my supervisors, Piyush and Mike, for assisting me in everything to do with my thesis. So yeah.